Hello. In the first talk, I tried to prove that the twins paradox and flat earth paradox in fact do exist in special relativity. I also proposed a reason for the existence of the paradoxes. In short, I blamed light clock. In this talk, I concentrate on light clock itself, trying to analyze its working characteristics and how to read it. There are some repetition from part 2 which I bring here again for the completeness of this talk. The light clock is the brainchild of Einstein. It is simply a pulse of light being bounced between two parallel mirrors L meters apart in vacuum. It is assumed that different observers can easily detect or follow the plain working of the clock. Therefore, this appliance has been the clock of choice in special relativity. The question here is, can we accurately and consistently measure time with this apparatus? To study this clock, let us consider a more elaborated version. The reason for this elaborated version is to be able to add a counter which I use at the end of this talk. The clock consists of two lasers A and B which are fixed in the center of two parallel circular plates in a cylindrical structure with the height of L. Two photocells are also fixed on the insides of the circular plates. We assume that when the upper plate receives a red light pulse from laser A, laser B immediately emits a blue light pulse and vice versa ad infinitum, as shown in the picture. Basic time measurement. Suppose the clock is at rest in all three perpendicular Cartesian directions, x, y, and z. In other words, we assume the clock is put in an inertial reference frame and observed from the same frame. The time for the pulse of light to travel between the two plates is L divided by c, c being the speed of light in vacuum. The effect of observer position. Case 1. Suppose the observer is positioned at point O1 inside the clock, which is the middle point on the line between A and B, as it's shown in the figure. Any light pulse from A or B reaches the observer with a time delay of L divided by 2c. The duration between any two consecutive light pulses spotted by the observer is TAB equal TBA equal L divided by c, where TAB is the time duration measured between observing a flash from A followed by a flash from B. We can call this a tick. TBA is the time duration measured between observing a flash from B followed by a flash from A. We can call this a talk. Case 2. Suppose the observer moves to point O2 on the middle of a side line. The observer is now outside of the light beam and practically cannot see anything to measure. But if he could see the flashes, they could be observed with a delay of L divided by 2c times square root of 1 plus d squared divided by L squared, which is the duration for light travel along the length of O2A or O2B line. However, the duration between the two consecutive light pulses detected by the observer in this new position is TAB equal TBA equal L divided by C, which is the same as observed in case 1. Case 3. In this case, the observer moves to point A. The time between two flashes detected by the observer in this new position is TAB is equal to L divided by C, but TBA is equal 0. In general, the time between two flashes seen by the observer in any point inside or outside the clock varies between 0 and 2L divided by C. In other words, the duration of a tick is not the same as the duration of a talk in Einstein's clock, unless the observer is positioned on a perpendicular line to the laser beams bisecting it at the middle of AB line. Let us call this line the tick equal talk line. The addition of the two measurements, tick plus talk, however, is constant for any observing point and equals to 2L divided by C. It can be concluded that an observer positioned anywhere within the inertial reference frame of the clock can only accurately measure time if 1. Observes the duration of two consecutive flashes from the same source as a unit of time, or 2. Staying on the tick equal talk line. This position is only theoretically possible. The existence of the tick equal talk line doesn't mean other observing points are not correct, rather highlighting a limitation of the clock. The measurement comes with a delay between a flash and its observation, which depends on the distance between the observer and the source of the flash. Now, what happens if the clock moves? Consider two coordinate systems, S and S prime. S and S primes are supposed to be inertial reference frames, and we suppose S is stationary and S prime is moving to the right with constant speed of v, and we suppose that the clock is in S prime. Case 4, a standard position. An observer in S sees the light clock moves to the right with constant speed of v. It is suggested that for the observer in S, the light has to travel longer for the round trip from A to B and back to A as shown. The time for the round trip is equal to T0 times gamma. Gamma is Lorentz factor and it is 1 divided by square root of 1 minus v squared divided by c squared. This indicates a moving clock runs slower. This is known as time dilation. As the speed of clock gets closer to the speed of light, the clock appears to run slower and slower until it freezes at v equals c. Equation 1 is the standard time measurement between two inertial reference frames in special relativity. Mathematics of special relativity also relies on gamma for length contraction and relativistic mass variation. Case 5. Turning the light clock. Suppose the light clock is turned 90 degrees so that the direction of beam from A to B is in line with the speed of the clock itself, v. For the observer in S prime, the unit of time is still the same, T0. For an observer in S, the light has to go longer from A to B and shorter from B to A as shown. The time for light to go from A to B, or tick, is equal to C times T naught divided by 2 times C minus V. And the time for light to go from B to A is equal to C T naught divided by 2 times C plus V. And if we add these two times, we get T naught times gamma squared. Now we can summarize the effect of the clock orientation. First, the direction of the clock affects the time measurement from a different inertial reference frame. And second, the difference is between T naught gamma and T naught gamma squared depending on the orientation of the clock. How should we deal with this problem? In special relativity, the help comes from length contraction. What is length contraction? George Fitzgerald and Hendrik Lorentz wrongly proposed that objects are contracted in the direction of motion relative to ether. Length contraction was put forward to justify the existence of ether despite of Michelson-Morley null result. The idea was accepted into special relativity, but between two inertial reference frames. That is, a 1 meter ruler in one inertial reference frame must be, not appears to be, half a meter according to the second frame, and half a centimeter or any other length between 0 and 1 meter from a third reference frame, depending on their relative speeds. It is thus argued that the length of the clock is shrunk by 1 over gamma in the direction of its motion. Thus, the clock timing should be corrected automatically according to its orientation. This argument relies on or prefers only one specific orientation of the light clock for time measurement, where the duration of a tick is equal to the duration of a clock. Widening gap between tick and tock. Which orientation of the clock is the correct one for measurement of time in S, knowing that the speed of S prime can be non-zero in any of the 3 dimensions of space? Depending on the orientation of the light clock and quantity of V, the duration of a tick and a tock in S prime can be enormously different and almost be any value if observed from S. The duration of tick can be between T naught divided by 2 and infinity, and the duration of tock can be between T naught divided by 4 and T naught divided by 2. Length contraction and the addition of tick and tock practically solves the orientation problem of the clock, but it cannot explain the widening difference between a tick and a tock, which is nothing to do with length contraction. Here it is shown that there is an obvious reason for these differences. Boat clock. Consider a canal in which speed of water can be controlled. Initially, water is standing still, V equals 0. 2 toy boats repeatedly travel from point A with the constant speed of u for the following 2 straight round trips. The first boat aims to reach point B across the river and return. The second boat aims to reach point C and in downstream and return. Duration of each trip is 2L divided by U. Both boats return to point A at the same time. Generally, the duration of any equal distance round trip is the same in any direction when V equals 0 and U being constant. This duration can be assumed as the unit of time. With water flowing at constant speed, the unit of time increases similar to the increase in the unit of time in a light clock moving away with a constant speed of v. The increased unit of time is 2L divided by U divided by square root of 1 minus v squared divided by u squared. And its relation to the proper time t0 is t equal t0 divided by square root of 1 minus v squared divided by u squared. The above formula is a familiar expression in special relativity, that is, Lorentz transform. It is used in time dilation and length contraction. What if the boat goes to point C in downstream and then comes back to point A again? In this case, the duration of A to C trip is equal to L divided by U plus V, and the duration of C to A trip is equal to L divided by U minus V. Duration of a return trip then is 2L divided by U divided by 1 minus V squared divided by U squared. And its relation to the proper time t0 is t equal t0 divided by 1 minus v squared divided by u squared, which is similar to the formula for time dilation due to the light clock moving with speed of v along the direction and then opposite of light. The relation between the two units of time is TACA divided by TABA equal to 1 divided by square root of 1 minus v squared divided by u squared, which is similar to the relation between units of time of light clock in the two perpendicular directions, which is t1 divided by t2 equal 1 divided by square root of 1 minus v squared divided by c squared. Summary of boat clock. The working principle of the light clock used in relativity is the same as the boat clock, where the toy boat goes back and forth with a constant speed of u from bank to bank or between 2 points along the river, a downstream upstream route. Similar to the light clock, one can, at least in theory, use the repeating travel of the toy boat as a clock. When water in the river is not flowing, then one can use the duration of each journey as the unit of time t0 or proper time. With water flowing with a constant speed, then the duration of the trip changes, and this fact is nothing to do with length contraction or time dilation. We now get back to our clock reading. So far, the clocks have been moving away from us. Now, what happens if the clocks are coming towards us, which is our case 6. For the observer in S prime, the unit of time is still the same, t0. For an observer in S, the light has to go shorter from A to B and longer from B to A as shown. The time for light to go from A to B or tick is c t0 divided by 2 times c plus v, and the time for light to go from B to A or tuck is equal to c t0 divided by 2 times c minus v, and the total time is again tv equal t0 times gamma squared, which is the same as the clock moving away. Now, what is the difference of the direction of the clock movement on varying time delay between any pulse and observer? Time delay between two pulses when the clock is moving away. For the observer in S, the clock is moving to the right with a speed of v for duration of tv. Suppose the first pulse is flashed with 0 distance from the observer. The second pulse is dx away from the observer, and the time for the second pulse to go from A to the observer is time delay, and is equal to tv times v divided by c. The total duration measured by the observer in S is thus t total away equal tv plus t delay, which is equal t naught gamma squared times 1 plus v divided by c. Time advance between two pulses when the clock is returning back. Similarly, the time advance for the second pulse is t advance equal minus tv times v divided by c, and the total time measured by the observer in S when the clock is approaching the observer is t total return equal tv plus t advance, which is equal t naught gamma squared times 1 minus v over c. Time delay advance in a standard position. In this position, no difference has been recognized between the clock getting away or returning. The main reason is that in both cases TV is also the same. However, no time delay or advance is recognized between the two readings from S. In fact, if the observer is at point O, the actual time measured between two pulses from laser A when the clock moves away is t total away equal tv plus t delay, which is equal t naught times gamma times 1 plus v divided by c. Also, the total time measured between the two pulses from laser A by the observer in S when the clock is approaching point O is t total return equal tv plus t advance, which is equal t naught times gamma times 1 minus v over c. In this slide, two sets of formula is given for accurate reading of Einstein's light clock. We should note that time dilation factor depends on orientation of the clock and the direction of movement of the clock. Both gravely affect unit of time. Now, what happens if we add a counter to the clock? We assume again that when the upper plate receives a red light pulse from laser A, laser B immediately emits a blue light pulse and vice versa ad infinitum. For the benefit of an observer, a counter is added to the bottom plate which increments when a light pulse is received from laser B. For an observer in S prime, the frame in which the clock is positioned, the unit of time is still t naught. From an observer in S, the frame from which the clock relatively moves with constant speed, the duration for the counter increment is the same as in S prime. The orientation of the clock has also no effect for any observer at any inertial reference frame. The only difference is either a delay or advance due to the direction of the relative movement of the clock. T away is equal t naught times 1 plus v divided by c, and t return is equal t naught times 1 minus v divided by c. This is acceptable and correct, and can be explained by the following examples. 1. Suppose the clock moves away from an observer with the speed of light. It reaches a distance equal to the distance from the sun to the earth and then stops. It takes about 8 minutes for the clock to reach its destination. When the clock shows 8 minutes, the similar clock in the observer frame shows 16 minutes. T away equal 2 times t naught. In its destination, the clock is always observed with 8 minutes delay, which is also true for the sun, as we always see the sun 8 minutes in the past. 2. If at some time the clock returns to the observer with the speed of light, the observer only notices this movement when the clock appears in front of his eyes. In that case, t return equals 0, which is again correct. And finally, here is the conclusions. Einstein's light clock is not a reliable time measuring apparatus from outside of its inertial reference frame due to the following reasons. 1. Duration of a tick and a tock depends on the observer position. 2. The moving clock shows different time unit depending on the orientation of the clock. The duration of time unit is also affected by the direction of the movement of the clock. Adding a counter eliminates gamma and corrects for orientation.